Good afternoon. So let's continue with the memory systems. Last time we introduced you the idea of caches, and today I'll review some of that material as well as show you how to actually implement them in hardware. And that's essentially lab 7 for you, where you'll be implementing a cache system. Okay, so we saw last time the idea of a direct map cache. So you have certain amount of cache memory, and you look at the address, and then you choose the lowest order bits in your address and decide which line of cache this word can be in, and you go and access it, right? So you have to be careful about how many, bits are used for index and how many bits are used for selecting from the line that comes out of the cache, because often we store more than one word. Typically we store anywhere from 4 to 16 words in a cache line. So this is how a direct map cache looks like, and by comparing the tag part with the value stored with the address, full address, you know whether you got a hit or not. So this is very, very important. And you know exactly how many tag bits you need, how many index bits you need will depend upon these parameters, and they are not very difficult to figure out, and they make for wonderful questions on quizzes. So make sure you understand how to do this. All right, so once we have a direct map cache, and this is really the very simplest cache you can imagine, many other things will follow from it. The biggest drawback of direct map cache is that if two different addresses you want to use happen to map into the same location in the cache, then only one of them can be cache resident. And that's called a conflict, because you want to use both locations X and Y, but it just so happens that because of their addresses, they happen to map exactly the same location in the cache. And when that happens, it's a conflict, and the performance can go down dramatically because of conflicts. So people have come up with more elaborate schemes for caching, and that is called set-associative caches. So whatever we had in direct map cache, I can duplicate it. I can have two direct map caches. And what I'll do is, when you give me an address, I will search in both of them and see if it's resident in either of them. So now a given address has two possibilities. Either it's in this direct map cache or it's in the other direct mapped cache, and that reduces the chances of a conflict in this. And typically we are talking about 2-way caches or 4-way caches or 16-way caches, or something like that. And the reason we don't just make it totally associative so that a word can reside in any word of cache, any slot of cache, is because it gets too expensive hardware-wise, and the benefits are not commensurate with the complexity of the hardware. So I hope the idea is very clear for set-associative caches. I'm showing it for the case 2 here, that you have 2 of them, you search them in parallel, and you see if you got a hit in either of them. And one invariant that has to be maintained in the implementation of this is you cannot get hit in both of them, because that's like saying a word is being duplicated, right? The same word, same address is resident in this direct map cache as well as that direct map cache. That's not allowed. All right, so a word, a line, whichever way you want to think about it, can be resident in only one of the ways, right? Not in multiple ways. But when it comes to storing it, we can choose which way we want to store this thing in, which way we should allocate the cache in. So you see all these things. If it's a hit, depending upon which hit you have, you will select that word coming out from it, and at most you can have one hit happening in the cache. Now let's think about store. So this is all very well if you're doing reads. You know, you will go and if you get a hit, you read the data. Now what is to be done in case of a store? So suppose store gets a hit, you know, it's in the cache, that line, then you will bring out the line, you first read it, modify that word, and then write it back into the cache. Make sense? Right? And if you so some people like to think that if I do this, then suddenly, you know, my cache is inconsistent with the backing store where the real data was, right? Because now I updated the cache, but I did not update the memory. And when we manage caches like that, it's called the write back policy, that we only work on the cache side. Only when there is no space left in the cache and I have to throw out a line, then I go and write it back. So that's why the name write back policy, in case of, you know, when you're trying to do a hit. And write through policy is, it's a little bit hard to explain why it may be a good idea, but you write in the cache, simultaneously you write in the back end memory. That way you keep the two things consistent. But there are two complications if you do this. One is that writing in the back end store takes a long time, right? And secondly, you're wasting bandwidth. I mean, if you're writing in the cache repeatedly in the same location or in the same line, you know, then you're wasting bandwidth. You don't have to write every time into the backing store in this. So write-through policies are used, but under very, very special circumstances, which I won't go into. For write-back, status needs to be invalid, clean, or dirty. Invalid means there is nothing to write back. Clean means it is something, the cache is occupied, but you don't have to write it back because the value here is consistent with whatever is in the backing store over there, whatever is there in DRAM. I keep using the word backing store, which can be confusing for different reasons. All right, so it's not there in the real memory, DRAM, it's only in SRAM. Now, the idea that is also very, very general and used in many contexts in architecture, actually in operating systems also, is the idea of keeping a dirty bit. So whenever you write into this cache line, I can go and mark it as dirty. That way I remember I modified it. What is the advantage of that? Now when it comes to throwing out this cache line, I have to write it back only if it's dirty. Because if it's clean, then by definition it's consistent with whatever is in the backing store. So this bit turns out to be quite useful for saving bandwidth, and it's almost always used in all caches. Now on a write miss, what I can do is I don't have it in the cache at all, right? So I can behave like a read. First I bring the line into the cache, and then I'll go and modify the word of line that I have to modify. But you say, why am I doing that? I mean, suppose I have a program where whatever I'm writing I actually never read, because or I'll read it much, much later. Not an uncommon scenario, right? That you may be creating something that you're not reading. So why pollute the cache with that? So in that case, what you can do is you don't write it at all in the cache. You issue a write, I look in the cache, it's not there. So instead of writing in the cache, bringing the line in, writing it, I just send it directly to the memory, just write it. I don't bring it in the cache. Things have to be in the cache only when we do loads. They don't have to be in the cache when we do stores, because we can just send it directly to the memory. So this policy is known as no allocate on a write miss. Okay, the most common case, and that's the one, if you have to understand one policy, set of policies properly in this class, it will be write back and misallocate. You know, so when you get a miss, you will allocate, write miss, you will allocate a design. So this is what we'll be focusing on in our implementation. Okay, so again an overview of loads and stores. When we process them, what happens? So what is our starting point? You're giving me an address. There has to be an address if you're talking of memory reference. And the very first operation we will do is search the cache for this address. Does it exist in the cache or not? Right? So there are only two possibilities. Either it exists in the cache, a hit, or it doesn't exist in the cache, a miss. So this is the highest level thing that is happening in the cache. If it's a hit, then return a copy of the word from the cache line. This is the fastest case. You access the cache, it is there, and then you immediately return the value that came out of the cache. Okay, and if it is a store, then you will go and update it. So remember, there's something slightly subtle about the store. You just don't go and write in the cache. You first read the line, modify it, and then write it back into the store. It's all implicit. It's happening inside the cache. Okay, bring the missing cache line into the cache if it's a miss. But in steady state, you should expect your cache to be full. So whenever you bring something in, that means something has to be thrown out. Okay, that's just common sense. And if you have a direct map cache, you know precisely what has to be thrown out, because the thing that is coming in, you know its address, so you know which line it will go in. So whatever was in that line has to be thrown out. So often may require writing back a cache line to create space. You know, so this is the general idea of whenever you are processing a miss case, and only then you can bring it in. And if you had a choice, if you had a set-associative cache, then you have to decide which one are you throwing out, the left one or the right one. If you have 4 of them, then you have a choice of 4 line to throw out, you know, from the cache. And then finally you update the cache line, etc. So you can see hit is very, very fast. Assuming SRAM can be accessed in 1 clock cycle, right? Literally, you know, you expect caches to work in, the good case should be it works in 1 cycle, 2 cycles perhaps, right? But that's the kind of timing you're looking at. But the moment you get a miss, it's a different story altogether. Because you may have to write something back, then bring a line in, and this latency is much, much larger. Rule of thumb is always assumes at least 10 times larger than the difference between the memory close to you and the memory that is far away. It can be even larger than that. So, you know, if you have to go back, it's going to take time, so therefore it always takes time to process cache misses. Other thing to note down about this is everything about caches is done purely in hardware. Okay, so everything I'm talking about, every policy, everything will be implemented 100% in hardware. There is no software involvement, and it will be totally transparent to software except for the performance. Okay, so in direct map cache, as I have said repeatedly, there is no choice, right? Every address has exactly one place in the cache where it can go to. All right, but in n-way set-associative cache, you essentially have a choice of n. An address can go into any of the ways, cache ways you have over there, and the moment you have a choice, that means you need n choices for line to replace in case you have to throw out something, and therefore you have to evict some line, and which line to evict. Often we hear of least recently used, LRU. If some line hasn't been used recently, throw it out. Or lines that are used, you know, keep them into the cache if possible. Okay, there are many, many policies for this, and if you have multi-level caches, policies we follow are actually different at different levels of cache. I won't get into that topic at all, but it will be a travesty if you took a lecture in caches and have not heard the word LRU. So LRU is a very common policy in caches, and not just in caches. LRU is a very, very common policy for managing storage resources at many levels. Okay, so Now, a two-way set associative cache can implement LRU with 1 bit of state per cache line, and that you may wonder, really, I can keep track of, which is what I referenced last. So can somebody explain me how you would use 1 bit to keep track of which is the most recently accessed cache line? Yep.
You just set it to like 0 if the one on the left is the most recently used, and 1 if the one on the right. Like each time you do an access, you check which one it pulls, and then you set the bit to 0 or 1, depending on which one it corresponds to from that.
Yes, I mean that will be a very good way of doing it, and that's one way you can implement it. So sometimes these words, if you don't think about them, imply lots of resources. But we as hardware engineers have figured out that we often use very fancy words, but when you look at the implementation, it takes only a bit or 2 bits or something, and that's actually quite important in hardware, because if it takes too many resources or if there is a long program to be run to decide something, that means it's not going to be done in hardware. It's going to be done in software. Okay. Now, cache performance is a very important topic, also a very difficult one. And people who design caches, they have to rely on certain things. So I want you to pay attention to what are the different kinds of factors that enter when we have to evaluate cache performance. So obviously there are so many variables available to you. So for example, what is the total size of the cache? Can I afford to have 1 megabyte of cache, or I'm going to have 64 kilobytes of cache? Obviously, if you have bigger cache, you're going to do better, right? So something else determines this. Chip area, cost, whichever way you want to think about it, right? So you would like to have as big a cache as possible, because that's what makes sense. But you may not have enough money, to implement a gigantic cache, or it may be infeasible. But once you have decided that you're going to have, say 64 kilobytes of L1 cache, now many other questions come up. What should be the line size? Should I work with a line size of 1 word, 2 words, 4 words, 16 words? And you say, well, that depends how much spatial locality you have, right? If you reference X, do you usually refer to about 16 things in its neighborhood, or on an average you only refer to 4 things in its neighborhood? So if you do not refer to too many things in the spatial locality sense in the neighborhood of an address, then it doesn't make sense to have large cache lines. On the other hand, you say, my gosh, my program is totally sequential, or my data accesses are totally sequential, then it will make sense to have a large cache line. So cache line size is a very, very important parameter, right? And almost all caches use at least 4 words in their cache line. The next thing in this is number of ways, right? How much associativity I want. So now you are definitely adding hardware complexity to it. Lines don't add too much hardware complexity, line size. But the moment you talk about two-way cache, essentially whatever mechanisms you had here are being duplicated. Right? So if the cache was organized as two-way, it's going to take more hardware. That's guaranteed. And what you have to balance it against is how much are you winning by doing that? How many conflicts did you reduce? By having a two-way cache or a four-way cache. And finally, the replacement policy. Suppose instead of LRU, if I used, some other policy, random, or something like that, or most recently used, I throw out because I expect it to be streaming. Whatever I have used, I'll never use again, so I throw that one out. All these policies have their place. So when you think about this question, I want you to keep 2 things in mind. One, there is decreasing importance as we go down in this. You never ask the question, what kind of replacement should I have? LRU replacement, or should I have 64 kilobytes of cache instead of 128 kilobytes of cache. First decision you take is, I can afford to have a big cache. Right? So you go down in this fashion in order to design your cache. The second thing is, anything I'm going to tell you about conflicts, etc., is not a property of the hardware. It's a property of the software. What kind of reference patterns are being generated by my program? I'm worried about conflicts. What if two addresses map to the same location? How often does that happen? Well, that question depends upon what kind of reference patterns are being generated by the programs you are executing. So it takes us a lot of effort to understand, the reference patterns that will be generated by a program. So for typical method of evaluation is, we have to figure out how many hits we will get given a memory reference pattern, and that different programs are going to have different memory reference patterns. So we have a set of such sequences, which we will use to evaluate our cache performance. All right, and once I give you this thing and I specify all the parameters listed above, then it's a deterministic thing. I mean, then you should be able to write a program that will tell you whether you're getting a hit or a miss. Okay, memory reference sequences are generated by simulating program executions. So we write a simulator, which you have already seen in in the assembly language programming classes. If we want, we could have sort of monitored exactly what addresses are being generated, during the execution of a program, and this is what I mean by the address sequence. So we can figure it out, what is the address sequence being generated in a given program execution. And number of hits, though fixed for a given memory reference pattern and parameters, is very tedious to calculate. Right? You will have to really, even for a moderately complex program, you will have to do a hand simulation of this. And what we'll do tomorrow in the recitation is we will show you some examples, right? That if we have this memory reference pattern and these are the policies we are using, for example, our cache line size is 4 words, and even if it's a direct map cache, it'll take you some effort to figure out how many hits and misses you're going to get. Okay, so performance evaluation, extremely important. I mean, that's why we have a design thing, but no performance evaluation is possible without actually running programs. So it becomes a chicken and egg problem. I'm designing the machine today, but I don't know what programs people will be running on it tomorrow. So the usual practice in this is we see what are the popular programs today and design the machines to run those. And often we turn out to be wrong, Nobody thought that, Instagram will become so popular, 10, 15, 20 years ago. So processors are designed and often they get put to use for different things. Final thing, which is also extremely important, is the idea of whether your cache is blocking or non-blocking. What do I mean by blocking cache? So if I'm getting hits, I don't worry about this. I just continuously get hits and I'm getting the answer back. But suppose I get a miss. Now I know it's going to take a long time to process this miss. So should the cache freeze to the outside world? Say, I'm busy, go away. Right? That will be a blocking cache. You say, I'm sorry, I'm busy processing a miss right now. But in a non-blocking cache, you can be more sophisticated. If there is a sequence of fetches you want to do from memory, if a sequence of references you want to do to the memory, even though we get a miss on the first one, we can look at the second one, say, got lucky, right? Got a hit on the second request that I'm sending into the memory. And let me process that, and you see that this can clearly be advantageous as far as performance is concerned. However, it's going to create a major headache because now the things will come out of the system out of order. Right? The first one got a miss, it's going to take half an hour before the result is produced. The second one got a hit, it came out in 1 microsecond. So we have to deal with that. So if we have non-blocking caches, we'll have a whole set of new problems, and unfortunately we don't have time in this class to get to that level of detail. But the thing you have to remember is we'll be focusing on blocking caches. At most one outstanding request at a time. Cache must wait for the memory to respond. Cache does not accept any more processor requests. And non-blocking caches, multiple outstanding misses are being processed simultaneously. Okay. All right, so now enough of overview of caches, and now let's get down to actual implementation. So we will implement a cache, one-way cache, right? This is the simplest one I can think of, right? Direct mapped. And it's a write-back cache. That means we throw out things only when for capacity reasons. We go there and there is no place for my value to be put, so I throw out that line from the cache. Write misallocates, so we do not send anything directly to the memory. We'll first write it into the cache and then wait for it to be thrown out to go back to the memory. And a blocking cache. So once we are processing it, we will not accept any new requests coming from outside. Is this, all these parameters clear to everyone? Okay, good. And this is the beginning of lab 7. So what you will do is you will do parts of this, and then you will really implement a two-way set-associative cache for your lab in this. So let's understand this stuff. So we start with the interfaces. So we have at least 3 different memories here. Memory as an abstract concept. Processor thinks of memory, right? In some way. What is the interface for that? And when we actually implement the memory, inside it we will find SRAM and DRAM. Okay, so let's look at the interfaces of everything. You have already seen the interface for memory. We send memory requests. What does a request look like? It's either a load or a store, and if it's a memory op, then you have to, if it's a load, you have to, for either case, load or store, you have to supply an address, and in case of a load, you also have to supply some no data, and for store, you have to supply some data in that. So this you have seen before already in the processor we were writing. So nothing is changed. This is the memory interface you're familiar with so far, and we do not expect stores to generate any response in this, right? Store is just, as I keep using this analogy, it's like launching a missile, you know, so you just send it to the system and it goes after that. You can't stop anything, right? It'll go and eventually get, a memory will get updated. Okay, now I have to actually worry about types in this, you know, and you want to think of this thing as in terms of parameters, but it gets very tedious and it will come in the way of understanding what we are talking about. So I want to minimize parameterization, and therefore what I'll do is we'll fix the addresses and the memory size and the word size as well as even the line size, right, in this, so that I don't have to continuously pass parameters, type parameters into this. Okay, so now what is the interface for DRAM? It also, you know, you send a request, except that DRAM interface is always in terms of lines. Remember, DRAM is the backing store for us, you know, so there is cache and there is DRAM. So processor is this side. So when processor talks to the memory, it's asking for words, right? Saying, send me a word, update a word. But what's happening in the back end is always in terms of lines. So I never have to think about DRAM being organized in terms of words. I will think of it as organized in terms of lines. So therefore I'm calling it a line request, a line address, and so on. That's the only difference between these two interfaces for memory and for DRAM. Everybody understands this? Yes? Okay. And also notice that I'm using action value interfaces for reading it, for getting the answers back. So until you pick up the answer from the memory, it's going to sit there. And the moment you pick it up, it's gone, from there. Because you can have different interfaces to memory where you are told the answer will arrive at 10 a.m. In fact, you're told it will arrive 4 cycles from now. And if you don't catch it at that time, it will be gone. Right? So I don't want to deal with that kind of interface. We'll hide those kinds of timing issues. We will assume whenever it's available, it will stay there until I pick it up. Good. All right. So it looks exactly like, as I said, like the memory interface. The third thing is SRAM interface. Now, as will become clear in this implementation lecture, SRAM is going to be used for many different things, because all these state bits I'm talking about, valid, whether it's dirty and whether it's writable, whatever state bits I want to have, they are also allocated in SRAM. So you will have SRAMs of different widths as well as different heights all the time, because if you have more memory, you would like to buy a bigger SRAM. So you have to, I'm specifically passing a parameter here. I'm saying, please make me an SRAM of a given size, and I will specify the size in terms of how many, lines it can hold, how many things of that data type it can hold. So that will be how the SRAM size will be specified in the creation of SRAM. Okay, so by now this picture, at least mentally, should be very clear to you. All I have done is I have put some interfaces on it to make it look like blue spec. So you have SRAM and you have DRAM. What is the interface for SRAM? You're getting requests from the processor side, and you will be reading something that will be going out, from SRAM. Similarly, SRAM at the back end talks to the memory, DRAM, in the back, so it will be sending lines to the DRAM and getting lines back from the DRAM. So those are the methods that are shown here, and these methods have to connect with each other. Processor accesses are word size, and DRAM accesses, the back-end communication is going to be in terms of lines. All right. Now, what I will assume is, because this is getting very, very technology specific now, that magically, you have some thing given to you which will say, make me a DRAM. All you know is that when you say make me a DRAM, it will come back with the following interface. Exactly how we do it internally is beyond the scope of this course, because that will require us to look into DRAM chips, how they are packaged and so on. And similarly, SRAM also, we will assume that when we make an SRAM, you will get something of a specific size, and we are specifying the size in terms of how many lines it has and what is the exact data type. So whether it's 1 bit wide or 1 word wide or 1 line wide, etc. So far so good, right? These are just the declarations for my cache. Okay, so I have said this, but I'll repeat it again. I will assume that we'll assume that DRAM has 64 byte or 16 word lines, and we will use line addresses there. Okay, so now let's understand the cache interface better. Okay, so as I said, it has 4 methods, 2 to do with the processor side and 2 to do with the DRAM side in this. Do these make sense? It's pretty trivial, request, response, right? That's what you are seeing there. These 2 have to do with the processor side, and these 2 have to do with the back-end DRAM memory that you have over there. No problem. Okay. Notice the cache size does not appear in the interface etc. This is by design. I mean, because this is not totally parameterized, I have fixed the sizes of various things so that you don't have to keep passing those things in the blue spec you write for this. All right. And this is kind of important because processor doesn't know how big a cache you have. In fact, we will do many experiments where we keep the processor constant, but we change the size of the cache, or we change the cache internally. So it's kind of important that the interface is not affected. If the cache size was reflected in these request responses going out of the memory, from processor to memory, it will be problematic, because then we'll have to change many things. We want to keep it completely hidden. Size of the cache does not scale beyond the memory, because it's a purely hardware thing. There is no software involvement in this. All right. Now to understand, peeling the next layer, I want to look at the cache organization. You already know that it has two methods talking to the processor side, two methods talking to the back-end DRAM stuff. Inside it, there is a very important unit which I'm going to call cache array unit, or simply CAU, right? CAU. Okay, so what else is there? So what you will find is that there are queues inside it, because this is working at some speed and DRAM is much slower. So sometimes you need springs, you need to connect things which are working at different speeds, and FIFOs are very good for that. You can just put the request in the FIFO and you will wait for the response whenever it comes back. So it just provides you some, you can take some shocks if you want. If suddenly you send 2 requests, it's okay, except that in our case, because it's a blocking cache, we will not send 2 requests. But that's a detail, right? It'll be helpful. But conceptually, there is a queue of requests and queue of responses coming in. All right. Now, similarly, once I have done the hit, once I have found the value for the request, suppose it was a load instruction, I'm putting it in this hit queue, and I could shut down at that point until you pick it up, right? Until the processor picks it up. But I'm ready to look at the next request if I want. So that's why this hit queue. Hit queue comes, we are done processing it. By we, I mean the memory is done processing it. It has the answer, but it will only disappear once the processor takes it. It's an action value thing. So you're providing some internal storage to hold the answers responses you have already generated over there. Now, as you can guess inside it, it may take a while to process a request. The best case is you come, you hit it, you put in the hit queue. But suppose you get a miss. Well, now I have to remember something about this request, because I'm going to send the request somewhere else. I'm going to send the request to the DRAM. And not only that, that's not enough. I may have to write something from here to there. It's going to take several steps. So I have to know where I am, in processing a miss. And that's what that state element is. It will tell me what state the cache is in. Is it waiting for the DRAM to respond? Is it waiting for something else? And those states will emerge for you. And during that time, we actually keep the request that was made to us. These two things together in modern jargon are often known as MSHR. But we will not use that jargon here. But if you ever hear the word MSHR, and I keep forgetting what it stands for, MSHR. Anyway, R is for register for sure. Okay, so, but conceptually, the state of the request and the request that is being processed, that is the information I need in this case. All right, so let's get on with the design of this, right? Let's first look at cache array unit. So what information do you have in the cache array unit? Suppose a request gets a hit, cache array unit returns a word, cache returns nothing if it's a store. If it's a miss, the slot must have been occupied. Now this is important now. If the slot is occupied, when you get a miss, you will get the whole thing coming out of the cache at that point. So this is what is already sitting in that. Why is that information being given to you? You were just requesting, something to find out whether it's a hit or not. You say miss, and not only it's a miss, this is the occupants of that slot. Why? Because we may have to write those things in the backend thing. So that's what is written here. In case of a miss, the data in the miss slot is returned so that it can be written back to the backend memory if necessary. All right, and when the correct data becomes available from the backend memory, then we will go and update the cache line. So that's why you have three methods here. You have request, you have response coming back, and response can be hit with data, it can be hit with no data because it's a store thing, or it can be a miss, and if it's a miss, then it comes back with lots of data. That was in that place. Very good. Okay, so you have seen the interface now. I've already explained all these things. You have a request going in, you have a cache response is going to be, a CAU response is going to be this whole, all the information that is across a line in that, and update action will be, I'll give you one such line and you'll just go and write it, whatever I'm giving you. So it's a pretty simple unit internally, right, CAU, but it has the real storage inside it. Now, this is giving you the details of all these values I just told you. So I already explained to you the hit-miss value. It is either a load hit, a store hit, or just a miss, because in case of a miss, I return the whole line. Okay, so this is just filling out those details for you. What is the exact definition of each one of these interface types that I have used inside it. Okay, now let's try to understand how this unit will work. All right, so this is just the basics of it. We are going to write this make cow module, and since I have already told you its interface that it has three methods, then our job is to write three methods on it, and we have to declare all the internal state, and if there are need for any rules, we will describe all those rules. So this is just a refrain. Anytime we have to implement something, anytime we have to implement a module, we look at its interface, and that tells us exactly what else has to be specified. So I hope everybody's with me and they understand what this means. And what is the very first thing you will do? You will write down all the storage elements inside it. So for example, you will have to instantiate SRAM for data array, tag array, and status array. Yes? Cache holds data, so of course, whatever the line size is, you will allocate that much. It has, status, whether it's valid, invalid, etc. And it has a tag array. What is in the tag array? It's indicative of the address that is stored in that line. Yes? It's not the full address because we can drop off some bits here and there, but essentially looking at that tag, I can tell what address is stored in this particular cache line. So these are three distinct things, and they are all being allocated. You have to instantiate three different SRAs. They are all of the same height, because if you are making a cache of n lines, then you have to have n everywhere in this array. All right. Now, this is the initialization status. Initially, it's ready to go. All right. And the current request will be whatever request is being processed And this is, I'm just shadowing, because this was already available to me outside. I'll just copy this value from whatever request was being processed outside in this. Now let's see how the request is going to be processed in this case. So initialize the tag array, data array, and status array. Store request R in the current request. That's how we will begin, processing this. Sorry, not initialize, I meant initiate reads. See, the difficult part here is the following. You got a request. Even to find out whether something is in the cache or not is not instantaneous. You have to read the index bits and then calculate, then see if there is a match in that or not, right? And because this is SRAM, you don't get the answer combinationally. You don't get the answer in the same clock cycle. You get the answer at the beginning of the next clock cycle. So that's why I'm using the word initiate the read. You will do all these initiations. You will start reading all these arrays, right? And you can imagine what will happen in the next thing that we do. Okay, and we'll store request R in the, and what is the last one, the request, my eyesight is so bad, response method, So in the response method, remember I have initiated all the reads for these array elements, and now I'm waiting for all I can't respond until I get responses, from all the reads. And then what will happen? What is the best case scenario? Anyone?
We don't get any list. We don't have any. We have all hits.
We are looking for only one, right? So we have one address and we get a hit. So if we get a hit, then that means I already have all the data because I had already initiated the reads, and I will read it, and I will take that data and I will put it in the hit queue, right? I'll put it outside. I'm ready to respond, from this because hit queue is outside. So now see what it says. Wait for the responses that you had initiated earlier. Get current tag, etc., from the response that came back. In case of a load hit, return the word. In case of a store hit, update the word. Okay. In case of a miss, return the data and tag and the status to the outside world. Is this clear to everyone what happened in this? The first one did almost nothing. It just initiated all the reads. At the time of response, I can't respond until I have heard back from everybody, all the things I had initiated. And in that case, the good news is I got a hit, I returned for the load case. For the store case, I immediately, fix the value, write it back into the cache, so I do that action. And in case of a miss, I said, oops, I returned the whole thing. So I have three different types of possibilities over here. Okay, and now what is the last one here? The last one here is that somebody outside is telling me they have gotten the response and this is the new line you're supposed to write back, so you're just updating that line. You're not reading anything at that point, you're just blindly going and writing into this array at that point. Are these three operations clear to everyone? Right? All the smarts of how we will use CAU is outside CAU. CAU is simply a dumb structure. I give something, it reads it. Right? If I ask it to write it, it writes it. Right? If I ask it to update it, it updates it. Right? So not too many smarts inside CAU. And now the question is, how do I use this unit, cache array unit, in order to build the cache I want, which is the direct map address? Yes?
Are there any guards for these three functions?
Sorry, say it again?
Are there any guards for these three functions? Or can they all execute in parallel?
You're asking a very good question, and what I will remind you, if most of the guards arise implicitly, right? So if something can be busy, right? So for example, exactly when can this response method execute? It will depend upon whenever these values are available. So you should imagine that there is, if like any other method, there will be ready lines coming out. Only when those lines say ready, only then this response method can be executed. Okay, and that will become its implicit guard. Yeah, this is actually a very interesting question, because these things keep getting conjoined at the right point, so it's almost hidden from you. But all these guards are all over the place. I mean, if you open it up, you will see it. So you will be completing this green code and everything in lab 7. All right, so now let's see what happens in the blocking cache in this. So we have described this cache array unit, so you can make it, right? Make CAU, and with a certain number of lines, and I have already discussed all these elements that I have a hit queue, status register, current thing, etc. So you allocate all these. Now the interesting part is you have to write all the rules now for this, because the methods are going to be very easy. The rules you have to write is, if the response that comes back, ready case is very easy. Ready case just passed on, just initiate the read in CAU. The interesting case is when CAU responds, when you read from CAU, 3 possibilities. You got a load hit, you got a store hit, you got a store hit, you will see nothing, right? Because it just success, it got written back. But load hit, you got some data back, and now you have to put it in the hit queue, etc. The most interesting case is you got a miss. And the moment you get a miss, you will go into a different state and say, oh, I have to send this back to the backing store. I have to also send a request to the backing store, to come back, and when the data comes back, I will go and write it. So that's what all these rules are that you will be writing, to complete the design of this. And here I have given you the methods for this. These methods are pretty trivial. That's not where the meat is. The meat is writing those rules written in green, and that's what you have to think about, exactly how they function. And don't try to write code unless you already know what you're doing, right? You have to understand at a high level before code will make any sense in this. And this is by far the most interesting one. When you wait for a CAU response to come back at that stage, these are the 3 cases: hit, miss, load hit, store hit, and a miss. What is to be done in that case? There is nothing I can do. I can read this code, but you can read it too as well. And as I said, this is what you're doing in lab 7. The performance question, again, you will have to analyze. Hit case is the most important one, because we expect to be hitting all the time. And if you are hitting, then we want to get the response back, and you have to count the number of cycles. Did it take 1 cycle, 2 cycles, 3? Every cycle matters. On the other hand, once you get a miss, if you add a few extra cycles here and there, it doesn't matter, because the miss is going to take tens of cycles, maybe 100 cycles. So if you went from 100 to 102, it doesn't matter for performance so much. All right, and that's this is the lab. 2-way set associative cache is what you're supposed to design. Very good.